Hello, everyone. My name is Fahad Al Hamdan, and today we're going to be talking about the interpretation of downhole measurements for geothermal services purposes. This chapter is basically talking about methods and issues that we face when we take measurements and gather data of a well. So let's just start with the introduction. As I mentioned, this chapter explores the problems that we face when encountered with downhole measurements, the tests, and processes involved as well. With petroleum groundwater, data is relatively easier to obtain for geothermal purposes, however. Directly testing for data is impossible to this day, so we depend on interpretations. So, to this day, we still depend on making a model based on whatever data that we gather and based on the best of our knowledge when it comes to geophysics, geochemistry, geology in general, drilling engineering, and environmental engineering. These interpretations can come from drilling operations, geology, downhole measurements, production tests, and data previously collected from nearby formations. So, if there was a field drilled in a close vicinity, its formation and geothermal properties will will likely be quite similar to formations if the proximity is within a few hundred meters, or if it exhibits the same um, behavior as the other, or as the different, or as the same field that we are looking at right now. Moving on with the introduction. Because interpretations are mainly dependent. Sorry, that was a mistake right there. Because interpretations are mainly dependent on data, two different sets of data may be considered to be correct. The physical factors that contribute to this are permeability distributions, reservoir conditions, and well design. Most geothermal reservoirs have a permeability distribution that does not follow any pattern and is considered random. The wellbore usually has an open section that can get up to 2,000 meters. So there have been multiple instances where, let's say, there has been previous data for uh, site X, and then another team would go into that same site, do the same drilling, and they would end up with different sets of data just because of how just because of the perspective of whatever team approached it. So one team may have used different methods or just had different assumptions and end up with two different sets of measurements, yet they're both correct in their own perspective or interpretation. Back down example. Now this is an example that was actually, this is a real life example. So an exploration well was drilled right into the central upflow. Outside this well are varying temperatures and pressures that are dependent upon depth. So temperature as a function of depth, Tz, and pressure as a function of depth, Pz. There's a vertical pressure gradient of 8.2 bar per 100 meters and hydrostatic of 7.4 bar per 100 meters. The difference in this value is what it takes for the flow to go upwards. So the difference between the vertical pressure gradient and the hydrostatic pressure gradient is how much pressure we would need to add to switch the flow from in a well or a well bore or even a feed zone from going downwards to going back upwards. If thermal equilibrium is found at any point in the well, then the fluid is in hydrostatic. If pressure equilibrium exists, the fluid is no longer static and there is thermal equilibrium between heat transfer in and out of the well and heat carried by the reservoir. So, thermal equilibrium is not that difficult to find. It's quite common in specific zones in well bores. Thermal equilibrium is the one good thing about it is that, as mentioned right here, it's hydrostatic, so it makes gathering the data easier and makes the process of getting the data easier. Objectives of the well testing program. So the first step would be to take the physical measurements of pressure, temperature, and flow. Furthermore, we are able to perform tests that give us data related to rock properties such as porosity, density, fracture geometries, and orientation. Every geothermal field is different and will require its own method of testing as its tests get further developed. However, the following parameters are generally looked for in every case: distribution of pressure, temperature, and permeability reservoir state, and finally, non-condensable gas content. Now, we will get back to, well, obviously, everything between pressures and permeabilities, reservoir state, temperature are kind of obvious reasons why we would care about these specific measurements and any kind of data that relate to them. However, non-condensable gas content may not be the clearest. We will get back to it, but just as a foreshadowing, it mainly relates to how much gas pressure is located at wellheads and how it mixes with steam, because in many cases water boils and becomes steam. Moving on with the objectives. Other individual wells may have these as defining factors in how the wells should be treated: location of feed zones, feed zone temperatures, undisturbed formation temperature profile, feed zone pressure, fluid type, production, and injection capacities. Now, of course, every case of, or every well is an individual case that would need to have its own, that would be a special case one way or another. And these measurements are examples of how each case or each well would be individual. So in some wells would need the feed zone temperature, others would need the production and injection capacities, or would need more detail about the production and injection capacities than other wells. When large-scale production starts, the program becomes focused on the changes and predictions of the following values: production temperature range, reservoir pressure change, production flows and enthalpies, changes in chemistry and gas content, changes in well performance, impact of production resource, impact of injection resource, and individual well problems. The multidiscipline approach. So yeah, as hinted before, well test programs are interactive and need a range of knowledge from different disciplines, which include geology, geochemistry, geophysics, subsurface measurements, production testing, drilling, surface plant design and operations, environmental engineering, and probably a few that I haven't mentioned right here. Even though these operations do require many or require extensive knowledge from many fields, from different fields that have to be interwoven to create a model or to have any sort of basic understanding, that I believe is leads to more problems, or leads to the process being slower, just because it's more difficult, I guess, to be able to, or it's more difficult to have to move on when you're waiting for many different aspects and many different teams that don't quite understand each other well to move forward. So that also leads to why we have so many problems, or why we face so many problems and issues when it comes to trying to model these wells. Measurements taken whilst drilling. Temperature buildup tests, formation pressure at permeable zones, permeability tests at loss of circulation zones. Yeah, now there are a number of tests that can happen or are possible to happen before actual drilling. There are tests that happen while you drill, and then there are tests that happen during production or during the first batch, let's say, of production. And even these tests themselves have to be designed and studied very thoroughly by this multidiscipline team that is looking at this well. Measurements taken upon well completion, which include temperature, pressure surveys, and injecting cold water into the well bores. Feed zone locations, permeability, formation, pressure, injectivity / productivity. Injectivity and productivity just basically mean how well the well can receive an injection of cold water or whatever fluid we need to test. Also, how well it produces. So basically, the capacity and permeability that are involved within these flows. After completion tests are done, the well is closed, heated up, and the following measurements are taken: formation temperatures / vertical temperature profile in reservoir pressures in the feed zone, and the location of these feed zones. Finally, a production / injection test is done. This is mainly to get the following values: measure production potential, measure downhole response, confirm feed zones or feed zone locations, and feed temperatures. Monitor other wells for a pressure response. So basically not to disturb the pressures of surrounding wells or fields. The aforementioned methods are only used based on what each individual case might need. Some will require all of them, some not so much. As mentioned before, there was just a section of individual tests that are not necessarily needed by many of them. Additional measurements that are or that would perform it, or measurements that would be taken after a while after the well has been in operation would be checking for mineral depositions, breaks, leakages. So basically, it would be more of we'll check if the geological field hasn't been disturbed, and as well as if the well itself is functioning properly and is still intact. Well models. So, I've been using this word throughout this whole presentation, but the whole point of the test programs and data records is to be able to make a model of the well and find the most appropriate way to approach it. These models include locations and thicknesses of permeable zones, permeability of the zones, reservoir pressure at each zone, reservoir temperature over the well depth, enthalpy of fluid at each zone, mechanical variations of the well. So these tests will, and all tests at each stage, whether it's pre-drill, during the drill, post-drill, and after production has started. All of these tests feed into us being able to create a model. Only in rare cases will all of these models be available. All of these, it's rare to happen that all of the information that we would like to have is readily available, whether we can test, because in many cases, testing methods that we have or that we use currently are not exactly possible. Temperature reservoir as a whole can be found due to conductive heat flow. However, pressures can only be determined at permeable zones. Now, this is a graph that shows how the calculated how different the calculated enthalpies and enthalpies and mass flows can look like, and how the actual mass flows and enthalpies can look like. Like I said, when we have some amount of information before drilling and before starting to operate, we can only calculate, interpret, or imagine a close approximation of what the well will act or behave, but we won't exactly be able to know how accurately the well will behave until after testing. And you can see that the dotted, the very dotted line that is the actual measurements that were are the actual measurements that were taken, and while the straight line is what we calculated them to be. So they're not too far apart, but then again, not exactly accurate. Some basic well profiles, conductive versus convective. Some of the basic distinctions between basic well profiles are conductive and convective. So one that happens via conduction and the other happens via convection. Now, conductive, impermeable rocks and heat is transferred via conduction, which results in a linear temperature profile with depth. So only the heat that already exists or heat that is being transferred through other fluids through impermeable rocks can transfer. And yeah, it is quite easy to interpret, but it's not exactly efficient or useful. Convective happens with formations that have permeability, and this is a far more efficient mode. Now, this is more efficient because when something is permeable, the heat in the fluids are much more easier to transfer and take less time, and geothermal energy ultimately utilizes heat stored in these geological formations. Some basic well profiles, isothermal. In isothermal models, many zones would have a constant temperature or even have a constant temperature increase with depth. This isothermal property can be due to a recycled flow within the reservoir or due to convective properties. So, in one example would be there is a well where starting at depth 960 and down to depth 1600 meters, the fluids everywhere in between the wellbore are completely isothermal. So they don't act, or they have the same temperature all throughout, and this mainly would be due to whether there was a shutoff in a certain place, or whether just the nature of the geological formation allows the fluids to cycle in that way. Boiling curves. A column of water in a well bore in which the water is at boiling point of pressure. Whilst flowing up, the steam can flow up the stream along the other non-condensable gases. Now, here is where we start to see why it's important to know about the content of non-condensable gases. In some cases, two-phase liquids enter the deeper feed zones, resulting in a stream of liquid water and steam in the production outlets of the wells. So, in some cases, in the feed zones, two phases of water or even of other fluids that exist there can flow up all the way through the wellbore and still exist in that two-phase form, which can cause a couple of problems. Now, because of the two-phase liquid buildups that can sometimes happen, as mentioned in the previous slide, they can depress into the casing, causing a pressure buildup on the wellhead. This is mainly caused by the amount of steam accumulated in the wellheads while water can still be boiling, and also the non-condensable gases. Now, when it depresses during at the casings, that can cause a slew of problems, anything from breakages, leakages, corrosion, And the amount of non-condensable gases that are there also add to that pressure. So understanding the content of non-condensable gas is crucial because the amount of steam that goes into that wellhead is ever changing. Now this is the final slide right here that will kind of weave together a lot of the concepts I talked about today. Temperatures in well WK10 in YRK. This example is an extreme case of how different measurement methods could show extremely different results. WK10 was a well drilled in YRK that showed that over the next two So WK10 was drilled in 1951, and then over the next 2 decades, they, as you can see in the graph, it showed that it kept cooling. This made sense to the drilling team since this well location was at the edge of the field, where in the edge of any geological field, this behavior is typically exhibited. However, they say temperatures were recorded at the same time every day and in the same location in the well, which gave results that were highly inaccurate. So they recorded every day, or every time they recorded 12 hours after the well had been up and overheating, and they always went to the bottom hole. So if the drilling team and the engineers had explored more different tests, then we would have had much more accurate results. And the BHC, the bottom square line, that is the actual temperature of the, or the calculated actual temperature of the bottom hole, had there been different tests and different data interpretations. And that is pretty much it. Thank you very much. I hope you enjoyed.